Okay, great.
Thank you.
So next we're going to hear from Dany Dumont about energy and momentum pathways in the marginal ice zone.
Thank you for the introduction. Thank you to the organizer for having me here and having the opportunity to speak about marginalized zone. I'm a marginalized zone enthusiast since a decade now, and I've been working with a group. And what I'm going to present here today is mostly done with my colleague Peter Sutherland at Ifremer. And PhD students, Jean-Pierre, who is in the room here, now postdoc in Grenoble, research assistants, and master students. So basically, the title was a way for me to kind of say something to this community and ask myself, what do we learn progressing in this complex subject? But I will really talk about, we'll make a case, try to make a case for wave radiation stress and what it can tell us about the marginalized zone rheology. What I remember from 5 years ago, and that was recalled today by Vernon and many more, we need more data, said modelers and mathematicians. And I'm a modeler by training as well. So yes, of course. And I remember really vividly John Dempsey saying that there are no analog for natural sea ice. If you want to study it and understand it completely, then study sea ice in its natural environment. So I don't say that we cannot learn from laboratory or from, but there, we need to go there. And I remember also saying to me back then and really now that to make sense out of that, like Sasha, we need to understand. And we need more, we need collective human intelligence, even though we can also use artificial intelligence to help us. So, okay, I'm really glad we talked, we've seen waves making their way into climate models. We have many more marginalized zone definitions today than 5 years ago. So I'm just gonna say a few words because about how we've seen the marginalized zone decades ago, and I'm really inspired by such images that we also seen. So here we are in Fram Strait, and we see that there is mesoscale turbulence and a lot of variations across scales, and the transitions from the open water to the inner pack ice here, and that was studied a lot from an oceanic point of view in the 80s and the 90s, where it was an interactions like the ice was considered a blanket, and that makes the wind stress, then impose a wind stress curl that input vorticity in the ocean that can link to, that can produce these eddying through instabilities or upwelling, downwelling, and eddying. So, and that matches quite qualitatively, at least, what we observe, and this is a probable mechanism. But yet, this study by Dye and collaborators in 19, they demonstrated that we can have the same behavior by just forcing, by throwing waves to the marginalized zone and using only the wave radiation stress. It induces like ice edge current. It forces a current along the ice edge, and then with the instabilities, you create vorticity and turbulence here. So this is the vorticity field after, in an idealized situation where you have waves coming in obliquely, and then it impacts the ice movement as well. They started with a, let's say, 1 meter ice, but it's really important to notice that they used Hibbeler rheology, VP rheology, and they initialize with a concentration that is slightly below 1. And for those who remember, when you are slightly below 1, the strength decreases a lot, which means the strength, compressive strength and shear strength is P here is low. So basically it's in a free drift, and it follows the ocean current quite well. So the wave radiative stress alone can generate ocean turbulence. So that leads to a point where we can have many causes to the same effect. So there are many causes to that effect indeed that are working. Those are making their way into models now. but it's already a point where you can force additional turbulence through waves only. So the way it forces us to approach the problem of the marginalized zone is thinking that is a coupled problem. So noting that waves here, they're not into coupled modeling because it's a complex, it's a non-local wind effect, as you can see like this. So wind blows over the ocean and the ice, for example. They input shear into the ocean, so they impose a current. But they also generate waves that will carry this momentum away from where they were generated and impose a force that is non-local. So then it will push on the ice and generate this turbulence that can be in producing any sorts of instabilities and vertical movements in the ocean. So now what I'm going to do here is just to try, and this is a complex situation that's really difficult to measure it all and say what is going on. You can imagine an experiment, oceanographic experiment, it would be virtually impossible to understand everything that's going on. So, so the goal here is to study the interplay between wave radiation stress and the response of the ice cover, the dynamical response. So the rheology term, in a sense, using like full-scale in situ process study. So it's not a laboratory study, but still in constrained conditions, in conditions where we can actually measure things or idealize the situation. And we extend that with a simple coupled wave ice model to extend these field results to a broader parameter space. So basically, I'm going to report on a paper that we published shortly after last, and I actually presented results, but at the time, 5 years ago, I really did not realize the impact, like the scope of what it means, what these results meant. And after that, Jean-Pierre just published in this special issue the modeling study. Okay, so that's our laboratory. It's the St.Lawrence Estuary. So we are here in that picture in January, it's -21. This is a polynya, so that means there's a ice concentration anomaly due to upstream tidal mixing that brings slightly warmer water. So there's less ice than elsewhere. So that, and it's faced west. So the dominant westerlies create often these waves here that impact ice that collects in two bays. And it's short fetch waves. So it's basically, we don't have a complex wave field coming from many directions. So that simplifies one thing. So we will be using that laboratory, and I'll come up with that. But let's say the conceptual or mathematical framework or numerical framework is this one, is the coupled problem. So of course, we're going to focus mostly on wave-ice interactions. So I remind here some equations that are, I admit, simplified already, but so E is the wave spectrum, wave energy spectrum, that propagates into a direction. And this spectrum is affected by a bunch of source terms. So you have the wind input balanced by wave breaking dissipation into open water. There are nonlinear interactions, and when it hits sea ice, you have scattering and dissipation, and you can probably explode that term into many more terms as well, depending on the processes. And as Vernon said, we don't quite know yet how to model this dissipation in sea ice, and we are also working towards that, but it's one step at a time, let's say. Okay, so we have the wave equation. So sea ice momentum equation, acceleration, and it's you have here a term with external forces and the internal response of the sea ice. And if we explode that term here, we have well, large-scale ocean surface elevation gradients. Sorry for that term. The ocean current, the wind, of course. Some have talked about the seabed ice interactions, so it's a term that is now included in the sea ice model that is not related here. And this wave radiation stress. So that's going to be important for the following. And the rheology. In here, I will just use like the viscous plastic, the general Reiner-Rivlin form here with the P term, and mentioning that eta and zeta are viscosity, shear and bulk viscosity, and I remind the yield curve here. Okay, so the setup, the experimental setup is basically this one. I think it animates. Yeah. So it's a drone picture, just a drone video showing the landscape. So we have one bay here where we work in this marginalized zone here, and there's a large bay, Bidra, that opens here. So we have it's the proper scale, since what we see here, the waves that are impacting are, you can see the selective attenuation. So you end up here only with the longest waves. This is probably a few hundred meters. It's not that long, but for this kind of waves, the typical decay rate is about 400 to 500 meters. So we can let's say see the whole scale here of interest. We have a quite stationary and linear ice edge. So that's the geometry of the problem. We have incoming waves, and that was going to be our x-axis along ice edge axis, which is y, and the tau here is the wave radiation stress that we're going to compute. And we have an instrument that measures currents as well, because wind and current are also other terms. But you'll see in the following that the wind and the current can be in some way neglected in the face of the wave radiation stress, or at least be measured. So let's say on paper that translates to a situation where we have the wave energy that penetrates the ice, which is the energy is independent of y, so it's homogeneous. It's fairly homogeneous along the ice edge, and it decays along x. And even if the incident angle is non-zero, and so the two equations, I mean the dynamical CS equations here reduce to that, because we are in stationary state, and we neglect so far the other source term, the other forces. So leaving only the wave radiation stress and the rheology term, the internal strength. And we can separate this problem into two directions. So into two equilibrium, one that is a compressive equilibrium, that is going to balance the wave radiation stress will balance the pressure term, and the shear equilibrium, where we can have a shear current along ice edge, which is balanced by viscous forces. So the 2008 paper, we studied the compressive equilibrium, and what we did is, let's say we didn't use like the Hibbler rheology. We wanted to have a rheology that applies to that kind of ice. So I show you the three main events that we worked with. It's not a land-fast ice cover. It's not elastic. It's a jumble of ice pieces in a soup of frazzle or slush, and that slush is coming in these days because we are in March during fairly sunny days, so there's no frazzle production, but it's mostly like the erosion of flows rubbing with each other for a long time that makes that rubber. It's not always like this. Those are examples. And what will be really important is that's what we see from the surface. But when you are on the ice and you try to measure the thickness, you drill a hole, I don't know. For example, you take that flow, you drill a hole, and then boom, you have another flow underneath. Boom, and then probably a third one as well. So they are piled up. So they didn't hear me. Okay. So I'll try to summarize quickly. So we use the Mohr-Coulomb friction rheology used by these authors in the past. And that leads to a pressure term that's proportional to thickness squared. So that's one message here. And that this is the internal angular friction. And you have a porosity term. So that also that takes into account the fact that you have water interstices between these blocks. Okay. Don't know what's going on. Yeah. Okay, and then the other term, so that was the rheology. The other term is the wave radiative stress tensor. There is much less tuning to that term. Basically, if you know the dependence, the spatial dependence of the wave energy field, integrated wave energy field, so over all frequencies, all directions, this is a stress tensor, and then you compute the divergence of that stress tensor, and you obtain that term here at normal incidence in deep water. And that leads to an expression where for the thickness profile, which depends on the wave attenuation, which will drive the radiation stress, and this KR term, which is the rheology. Yeah, so basically that's what I just said. Remember that in KR you have porosity and internal friction angle. So we picked, first we picked the possible values from the literature, and we measured that, the wave energy decay with wave buoys. Actually, I'm coming right now at it. So this is laboratory. This is one, let's say, configuration of event here. And what we do is, yeah, it has started. Sorry. So this is one typical event. So we have buoys deployed along an even close to the ice edge here, deployed with an ice canoe. You can see a gradient in the flow size distribution. You can see also other things like the rafting. You see overwash and flows on top of each other, and probably also flows below these large ones. Of course, it is already broken up. We haven't captured the breakup event for that. And then we measure the thickness. And when we measure the thickness, it's not the thickness of just one flow. We try to measure the thickness of the ice jumbo with a meter stick. So the data, you'll see the data, but we don't have millions of data. So we should do an averaging of that. And so those are the 4 events we analyzed. So the deployments with the canoe, here the attenuation from the wave buoys from the outer, from the ice edge inward, and we compute the attenuation coefficient. And just before going into the thickness result, we could also, by putting wave buoys close to each other within a wavelength, measure the dispersion relation, which here you have the open water, deep water dispersion relation. This is the flexural dispersion relation. So if the ice would have been elastic with some Young's modulus, of course it can be different, and the mass loading dispersion relation. So it follows in this case like the open water dispersion relation. So there is no evidence for scattering that we measured. And this is the scatter of wave attenuation that we also measure. And here wave attenuation is really the decay of the wave energy, which could be the sum of all these terms that you see. But over really short distances, nonlinear interactions, wind input, and so on, they are negligible in the face of other dissipative effects. So we could think that empirical curve followed the dissipative processes. And this is for reference the Malin et al. Let's say empirical fit here. So it's almost 1 to 2 orders of magnitude higher here. So if we we plot our thickness measurements. You see the dots, you see those are averages, and this is an estimation from the dispersion relation. So it follows quite nicely the normalized thickness compared to normalized with the equilibrium thickness, because we have different wave energy. So we normalize all this. And so that's a way of saying that, okay, the model is right. But if you do the exercise inversely, so you know the thickness and you wonder if it was a Hibbeler type rheology applying there, you would end up with this curve here, while so the ice thickness we measured is indeed for one event around 60 centimeter far from the ice edge, and following that kind of distance. So within 100 meters, most of waves were attenuated and we reached the equilibrium thickness. But the Hibbeler strength would have led to practically no thickening at all here. So I just, and I omit the concentration dependence because it's a fully compact MIZ. So basically, wave radiation stress near the ice edge is really strong, stronger than the wind. The wind is a cumulative effect through the compressive forces. So eventually the wind will be stronger, will impose a stronger push on the ice because it accumulates over long distances, but short to the ice edge, here you have the wave or wave plus wind strength. And that leads to a length scale that corresponds to the point where these two will compensate. The wind force compared to the wave-induced force, which will reach a plateau. So this implies as well that the MIZ is compact, and that can lead to up to 40 kilometers. Just to note that with another student, we measured with a ROV the profile beneath the ice. So they are to show the evidence that you know what we see flows here that are underneath, that are not on top. So really, waves can pile up ice quite. How am I doing? 3 minutes. So what we did is, what Jean-Pierre did is to look at the effect of having this collisional rheology here. That is the yellow curve, which is quadratic, compared to the linear Hibbeler rheology. And what we show, it's not showing, but this is the Hibbeler rheology, and that leads to, of course, significant, much more significant displacement of the ice edge and thickening of the ice as well. And the obtained ice profile thickness resembles this shape compared to the Hibbeler type, where that remains really thin and then compiled really far from the ice edge. This is the scale, and shear equilibrium, I will be short because we only posed the problem, and this work is ongoing, but just saying that we can also balance the wave radiating stress with the shear term, and we can this way quantify the effective viscosity, the shear viscosity. And how we do that is by using drone video. So what we see here in such a video, so it's the total velocity, which is the average deformation plus the orbital movement induced by the waves. So we can use the orbital velocity to compute the wave spectrum attenuation, and the deformation field to compute that one here, that term. So that work is ongoing. So take-home messages: we constrained the equilibrium model between the wave stress radiation, and it led to, let's say, the conclusion that a Mark-Coulomb frictional model applies really well. But remember the quadratic the dependence on H that is really different from the Hibbeler model. Porosity is something to have in the back of our mind, and that's it. So maybe if I have time after that, I can show, but that we gathered the evidence that the same thing happened at larger scales. So we were in the Arctic last fall, trying to do the same experiment, but now the scale is much longer. So it takes much more time and logistics just to deploy our buoys and measure things. And they are much more complexity, like multi-year ice flows, icebergs, scattering and generating turbulence and so on. But basically, we saw also rafting. Frazzle is really important as well. And we were in ice forming conditions there. So a last word on this, coming back to like the whole picture of the marginalized zone. So we looked at what happens here, but we also noticed that here waves play a role as well by redistributing the frazzle ice and collecting it. And what we've seen as well, and not yet really well documented, is that frazzle ice is pushed also under the ice quite strongly, and as long as there's a stress. So we assumed in our model that the stress is only applied to ice, but there's no reason that it's not applicable to the ocean as well. So it relates to some of Agnieszka's work that we want to do, and we are developing the technology to measure what's going on during frazzle formation in these windrows, turbulence-wise, like what are the flux, how the frazzle presence modulate the heat exchanges and salt exchanges with the atmosphere, and how frazzle ice collects with that. This is the instrumentation. And just, I'm gonna go fast, but implications of these results to the relationship between momentum pathways and energy budget in the climate system for short-term application. You see that if you push more sea ice, then and you mix more energy here, there's gonna be like feedback with the ocean and ocean atmosphere heat fluxes. And it happens in regions, Antarctica, Labrador Sea, Greenland Sea, in regions that are close to deep convection that are crucial for the AMOC and overturning circulation, not just the Atlantic. But so yeah, I want to thank you right now.
Okay, so I think we'll squeeze in one or two questions whilst we start thinking about switching over. To the back first.
Thank you, Dany, for a very nice talk. You show the data for the wave dissipation, which is like 1 or 2 orders of magnitude lower than Mike. How much?
Higher.
Higher, lower, yeah. How much fixated should we be about the? I mean, because the slope was correct; it was the omega cube.
Yeah.
Like, why would you have such a range of values that differs? Is it because Mike did a different scale where waves are long?
No, because Mike, I mean, the green curve I showed is an empirical fit to data. Data that comes from different sources, mostly oceanographic expeditions, ONR, and so on. So I don't know all the details, but one hypothesis is, so we don't know the thickness, for example. So thickness of the ice can modulate that. And we see that our data are really scattered as well. Data, but also I imagine that if you have two buoys really far apart, then how do you constrain conditions in between the buoy really well? So do you know if it's 100% concentration? If not, then other things can happen to decrease the apparent attenuation coefficient. While here, I mean, we were at a walking distance from our buoys, and we could see that the concentration was high, and we could characterize the thickness and so on. And I believe that these data are more close to the dissipation in the ice than what Malin is arguing that shows apparent dissipation or apparent attenuation. But it's an open question, really. Yeah.
Thanks, Dany.
Oh, yeah.
Great talk.
So.
Dany. Okay.
Yeah.
So I have a question about your simulations. You used different dependencies of the ice strength on the ice thickness, h for just linear for Hibbler, h squared. So the h squared comes from the gravitational potential energy stored in ridges, but you mentioned this is quite a deformed region.
Yeah.
Mark Hopkins has done discrete element simulations, okay? And when you take into account the friction additional to gravitational energy, that power drops from 2 to 3 on 2, okay? So looking at 3 on 2, I would imagine you get something between the linear and the squared, but it might be a better fit.
Maybe, yeah. Maybe, and that what we did for the modeling study as well is that, of course, if you just carry out this more Coulomb or h squared all the way up to 40 kilometers in ice, then you crush everything, which is not realistic. So that's why we kind of have a hybrid. So the third one is probably closer, like a mimic of Hopkins. Oh, sorry.
Okay.
Like this
I don't know
one
what that looks like, but if I was if I was going to choose one, I would have chosen 3 on 2, I think. But that might look more like your hybrid one.
Yeah, but I have to revise the underlying hypothesis of Hopkins for this, because like it happens also. So the thickening is not always happening in one ridge. It happens because of a force that, it's not a plastic deformation. Let's say deformation is like more progressive, so it thickens more homogeneously over a large distance.
Well, you mean like rafting over bridging?
Yeah.
Well, that will still lead to 3 on 2.
Yeah.
Yeah.
Great.
Do you want to get the video switched over, and we'll just do one more question?
Thank you.
Going to do a question.
Hi, Dany. There's
sorry.
one last question about the switch. Sorry. When you use your more Coulomb, like you weakened it with the porosity to take into account the fact that you had ice, and so in the Hibbler, like you had no ice thickening. But what if you included the same porosity to weaken the ice? What happens then?
Yeah. So I mean, my point here is like we have to revisit maybe what happens in such a flow size dependent rheology term added to Hibbler that will weaken the ice in these conditions. And whenever you hit a really large flow that's not broken, then it might be stiff enough, like even if it has the same thickness, for example.
Yeah.
So like the way to include flow size in the current rheologies is, I think, really a good way forward. Yeah. Flow size or damage or.
Thanks.
Excellent. Thank you.
Okay, great. Thanks very much, Dany. And we'll just wait for the switch over.
You got a phone, maybe?
Yeah.
Yeah, don't put that anywhere near. Because that's all the noises that I get.
Let them know.
Yeah. Because it uses 16.
Recording in progress.